So I hope you can see my screen,
Yes.
and I hope I am audible. So today I will talk about the notion of independence of events.
3:30 plus 1 hour কত হবে?
Sorry,
3:30 plus 1 hour.
I'm not able to understand. Did you ask if my lecture is for 1 hour?
Sorry, sir. My mic was left on.
Oh, sorry. Okay. Independent of events and completion. So I'm after discussion on these notions, we will work out some problems. Okay. Completion of completion and product. These are the notions, products of probability spaces. Let's see. So suppose that notion of independence of two events, I'm sure you have seen before, but let me say that again. Suppose that omega, you start like this, P is a probability space, comma, and A, comma, B are two events. We say that A and B are independent events, if you like, if probability of A intersection B is same thing as probability of A times probability of B. Okay. So this is the thing. And suppose that, so you can generalize it to your family. Suppose that, let us say A alpha, I don't know if I should say A alpha. Okay, let me say that E, scribbled something. So E is a family of events, AJ, need not be countable. So J in capital J is a family of events. Okay, so of events. We say that E is an independent family if, so suppose that A1, AN are distinct members of E, then probability of A1 intersection AN, this is equal to product of the probabilities AJ. J is equal to 1 to whatever N. Okay. So this last condition, this is equivalent to saying for any A1 AN in E pairwise distinct A one is independent of A2 intersection A. Okay. So this is a notion of independence, and I'm sure that you all have seen the first condition here. This you must have seen already. I'm sure you have seen this. Uh,
Sir,
yes.
sir, can E be countably infinite? E, the family.
Yeah, it could be countably infinite. Yes.
Okay.
But here you just do this only for finite things, finite number of things here. E can be countably infinite, sure, or E can even be uncountable, we don't care. E can be infinite, yes, definitely. Okay, yeah. Uh, so, well, I mean, this is motivated by the consideration that if you have a fair coin, successive tosses of that coin, when you look at the outcomes are independent. Okay, so we have intuitive notion of what it means for two events to be independent. This is not to be confused with two events being disjoint. So um, uh, yeah, justification for this uh, formula here, I mean, one doesn't just simply write a formula and then demand, I mean, make a definition out of it or anything like that. They're all, of course, people are led to that by practical considerations. So, what does it mean to say that two events are independent? Let us just discuss that and understand. Okay, so the intuition behind this. So, you say that A and B are independent if uh, the knowledge that the knowledge that B has occurred and does not in any way change the probability of A occurring. See, usually, so let's assume for this purpose that B has probability. So suppose probability of B is positive. So that is not a null event. Sorry. So you know it is not a null event. Okay. So you know that a certain event has happened, and that doesn't in any way change it, improve your knowledge of how frequently A is going to occur or what is the probability that A would occur. Okay. Whatever this information is independent of your knowledge of uh, A occurring. That is why. So, how do you suppose, since I said probability B positive, so it makes sense to ask. So, the whatever I have written here can be mathematically written as probability of A given B is same as probability of A. But you know that probability of A given B, but probability of A given B by definition, probability of A intersection B divided by probability of B. Okay, so that uh, so therefore probability of A intersection B is equal to probability of A given B times probability of B, which is same thing as, well, which is same thing as probability of, okay, yeah, product times B. And you can reverse the steps if you just apply the previous definition. Okay. Providing, of course, probability of B is not equal to 0. So that is something that you need to know before you can say, talk about conditional probability conditional on B occurring. Okay. So let us do one problem. So this is taken from the book. Suppose that two a die is thrown twice. Okay. Let S denote the sum. The sum of the numbers shown. Numbers shown. Okay. Let F be the F. Well, okay. Fj be the event that the first throw results in J. In J. So of course J is a number between 1 and 6. Yeah. Okay. So show that the event that the sum equals 0, sum S is equal to 7 is independent of the independent of the event that the first throw, that independent of the event Fj or any j. Okay. So it's a very simple calculation. So you know that the sum is 7. So let us write that thing as favorable events as S7. S7 means what? So the first throw can result in anything. The total should add up to 7. So 1, 6, 2, 7, 2, 5, so on. The first digit actually determines the next one if you say the total must be equal to 7, right? So we write that. 3, 4, since it's a small list, let me write it 4, 3, and then 5, 2, and 6, 1. That's it. And what about Fj? So Fj, well, the first throw resulted in J, and you don't know anything about the second coordinate. Let us write it like this, since I want to be, yeah, K can be anything. Okay. Now you want to show two events. These two events are independent. You just compute the intersection before you compute even the probability. S7 intersection Fj, this is equal to, well, first coordinate is j, the second coordinate has to be 7 minus j. And of course, 7 minus j is possible. Okay. So we have listed here everything. J is one of the numbers, 1 to 6. And what is the probability? Now you compute the probabilities. Probability of S7 intersection Fj is 1 by 36. Correct? And probability of S7 is 1 by 6. And probability of Fj is also 1 by 6. Okay. So therefore, you just compute the individual numbers and it fits into the definition. Sorry. I should write Fj here. Fj is equal to probability of F7 times probability of Fj, irrespective of what J is for any J. So this proves the required result. And I want to do another problem. This also from the book. So suppose that, let me see, I check after this. Something. Yeah, okay. Suppose that omega is 1, 2, 3 up to p. P is a prime. Suppose that A and B are independent events. Show that, well, A is either empty, let us say B not equal to empty, okay. I don't know, I may not state the problem as given in the book exactly, but anyway, this will work. A is empty or A is a whole space omega. Well, if A is empty or A is a whole space omega, there is nothing to prove. And let's also assume that B is not the whole space, okay. B is a proper subset of omega, okay. So given these things, suppose that A and B are independent, A is neither empty nor the whole space, then A has to be empty or the whole space. And what is the information given to you? Okay, so I forgot to say, getting ahead of myself. Okay, show that this, given that probability of any I, let me just simply write it as I is 1 by P. Any one particular sort of what is called elementary event or simple event is exactly P. Okay. So this is given to you. So what is the proof? Probability of any E is of course cardinality of E divided by so some people are not used to writing this. Cardinality, sometimes we write absolute value, divided by P. Okay. Now, what you do is, so you just write, so suppose A is also not equal to empty, A is also not equal to the whole space. Then probability of A intersection B is equal to cardinality of A, I see. Intersection B uh, divided by, sorry, not divided by, yeah, okay, divided by P, that's right, divided by P on the one hand. So if A and B are independent, then probability of A intersection B, probability of A intersection B, this is equal to, I'll write quickly, probability of A times probability of B, and this has denominator P square. And the numerator is something each one of these factors are less than P. Okay, so this is a contradiction. A, if A and B are independent, then this is equal to A intersection B divided by P. This is equal to some number divided by P square. But P is a prime number. You see, you cannot have this. Okay, since P is a prime number, you can transpose, cancel one factor P, it can convince yourself. Since P is a prime, this is impossible. So you get a contradiction. Therefore, one of the two must happen. A equals empty or A is a whole space. Okay. Yeah, so here is one situation. It's a very interesting problem. So suppose that, so this following problem illustrates that you can have collection of maybe some n number of objects and bigger than or equal to 3. Pairwise, they can be independent, but together they are not independent. Okay, that's very much possible. So here is an example. Is given in the book as an exercise. I just want to discuss this exercise. So, so suppose that a coin is tossed, a fair coin, actually, is tossed n times. It probably doesn't matter whether the coin is fair or not, but you know, tossed n times. Let so n bigger than or equal to 3. N bigger than or equal to 3. Okay. Let Aij be the event that the ith and the jth toss yield or show the same result. Same result. Head or tail. Okay. So this way you get a collection. Okay. A, I, J, 1 less than or equal to I less than J, less than or equal to yes, N. Okay. So you have this many. Show that. So let us call this our E. Show that any two members of A, members of E are independent, but E is not independent. Okay. Okay, how do you do this problem? You just keep computing, that's all. Okay, so solution. It's not my intention to do all the problems in the book, but initial stages, I want to go a little slow and work out quite a few problems. And as we pick up pace, many more problems are left to you as an exercise. And also, I will give you some worksheet, and this will also act as assignment sheet. Except that only some problems you need to submit for assignment. The worksheet will have many more problems, and they are for you to practice. And you are strongly urged to practice try as many questions as you can from the worksheets. Okay, so solution.
Sir,
Yeah.
sir, I didn't Just the last part I didn't understand. The set has to be independent with respect to something else, right?
Any
With
two members, any two members of E are independent. See, E is not an event. E is a collection of events.
yes, sir.
So it makes sense to say, well, I take Aij and then maybe AKL, and I want to show they are independent events.
Yes, sir.
Okay.
What
But
it
E
means to
itself is a collection, and therefore it makes sense to ask when is this collection of sets independent? That makes sense.
Okay. Yes, sir. That was what I was asking.
Okay. So, it's
so
like saying when you just have only two members, it's like you can form a collection consisting of two elements, two members, A and B. Okay. So,
Yes, sir.
that's okay, fine. You understand. Okay. So, let us consider. Yeah. So, consider, not let, but consider. So, you should also learn how to write these things. So, I try to write full sentences only so that you will learn also how to express yourself. Sometimes in the test and assignment, you just scribble something, just write only the mathematical thing, and then the connecting words are missing. We don't understand. I mean, it's difficult to figure out exactly, what you do, and and without explanation, everything looks sort of not clear. I mean, that you have understood. So you should also learn to express yourself. So sorry, I keep talking like this. I hope this is not a waste of time. So consider Aij, AKL. Okay. And the pair Ij is not equal to pair JKL. That is what it means to say I take two distinct ones, two distinct members. Well, okay. So we need to, okay. First of all, what is the probability of Aij? Is equal to, well, whatever be the ith thing, it could be head or tail. I want the same thing occurring in J also. And so that is 1 by 2, correct? Is that correct? You understand? It's not like it's 1 by 4, you see. So you note down what your Aij is. Aij is set of all, you see, this, I mean, we don't know what x1, x2 are. So xi, blah, 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 xj, xn. So I am writing this for those who don't understand this immediately. So xi is either so let's write here xr. xr is either a head or a tail. Okay. Okay. So all possible things, but subject to the condition xi equals xj. So you see, you will have either head. So only possibilities are, so head or tail. If it is tail here, it should be same tail here. That's it. Other things unconstrained, whatever it is. Okay, because on other things there is no constraint. XR is anything, either head or a tail. The only constraint is given here. Mind you, when I write IJ here, of course I and J are given numbers, and so it is given number. But when R is unrestricted for all other R. Okay. Okay, so that means about, so this is one n tuple, this is another. Okay, so I think I've said enough. If you are not convinced, you have to, you see, what are the possibilities for x1? There are two possibilities. So if you want, you can write here 2 power n and then just cross check 2. And then for xi also, ith factor also is 2, but jth factor is now determined. So this is a jth factor. And then remaining factors are all 2. So this is exactly 2 power n minus 1 by 2 power n, which is 2. Okay. Now let's move on. So of course, probability of AKL is also equal to 1 by 2. I mean, okay. So what about AIJ intersected with AKL? There are two cases to consider. One is k equals I, or other one is k not equal to I, and likewise j equals L, j. Of course, one of them must be distinct. Okay. So suppose that. So suppose it really doesn't matter, but you have to exhaust all possibilities. K equals I. Then automatically L is not equal to J, because you have the Aij, the I comma J is not equal to K comma L. So if one coordinate is the same, the other coordinate has to be different. Then, and what about Aij intersected with AKL is the event that the result of the toss at I, J, and L of the toss at the thing or the L occurrence are the same. Result of the, so let me write here properly. Else ith, jth, or else toss are all the same. Okay. So what is the probability of this happening? Probability of Aij intersected with the probability of, I mean, Aij intersected with AKL, same as probability Aij, AIL. This is equal to, so the first one can be anything, but that determines the resulting one. Okay, so that means you are essentially you are tossing the coin thrice, and whatever is the first one, you want the other two to also have the same, and that is 2 by 8, which is 1 by 4. Okay, and this already shows that, therefore, okay, and this is probability of Aij, probability of AKL, AIL in this case. Okay, so Aij, AKL are independent, AIL are independent, are independent. What about if, so next case is, so suppose that, well, J equals L is the same as before, so I don't discuss that. So suppose that, okay, I is not equal to K, write it very clearly. I not equal, first coordinates are different, second coordinates are also different. Then what is Aij intersected with AKL is the event that the ith throw is the same, results in the same as the jth, that the ith toss and jth toss result in the same outcome, whatever it is, head or tail. And so the kth toss kth toss and lth toss result in the same thing. Same. Okay. So, but the main thing to notice is that it could so happen that ith toss is a head and the kth is a tail, or it could be this is ith is swan and so on. So there need not, there is no, I mean, connection. Okay. So if you, so how many are there? So probability of, should I don't want to expand this, but just probability of Aij intersection AKL. So how many constraints are there? Whatever be the thing, there is one constraint, and whatever be the kth toss, that must be the same as lth toss. So only two constraints. Okay, so that's 1/4. In other words, you just keep tossing. You just check if the jth and the ith toss are the same. The jth, see we are going to assume that I less than j. Of course, k, we are assuming that already. The jth toss must be the same as the ith one. That only constrains j. It doesn't constrain k or l. The kth toss, whatever it is, that must be the same as the health toss. So after you toss your thing coin for the kth time, the health thing outcome is determined. So that's exactly, only two coordinates are fixed, and that means that it is 1/4, and which is also the same. So you just go over this argument in your head later on, after the talk and so on. And if you don't understand, please ask the tutorial instructors. On the other hand, if you take three of them, the problem says that it's not true. Of course, n could even be equal to 3, and the only way is, well, you just take, okay, I shouldn't say only way. Just take A12, intersection A23, intersection A13. What is this? Probability of this? This is equal to, so, so one, see at the first toss, it could be head or a tail, and the second toss, this constrains the second toss to be 2, and this constrains the third toss to be also 2. Okay, so third toss, what if this is head? I get head, 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 and if this is tail, I get tail, tail, tail. So how many possibilities? I don't get, so there are exactly two ways in which this can happen. So 2/8, which is 1/4, not equal to 1/8. That's the main thing. You see, the probability of the intersection must be equal to the product of the individual probabilities. But individual probabilities, as we saw, they were always 1/2. But I took three of them, and there are two distinct ways in which this can happen. It could be either a head, 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 or tail, tail, tail. So if you like, I can write that A12, intersection A23, intersection A33, A13. This is equal to, so H, 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 or tail, tail, tail. That's it. Okay. Yeah. Okay. How much time? Okay. I wanted to also talk about the other thing. Maybe, I don't know if I should do more problems or Okay, I'm a little confused because there's not much time. Okay, it doesn't matter. Let me do some more problems. I think that's better. I don't need to rush through and here is an interesting problem. So you see, this is a I tell you why this is an interesting problem. Uh, so this is another, I don't know, I lost track of the number. I should number them. I think I should just put some numbers somewhere. Okay, so I just maybe call this a first problem, maybe, I don't know, number 1, 2. So you know where the problem ends in 3. Okay, let us do number 4. Okay, so the- I want to do 2 more problems at least. Let us see if I have. So let n. So you see the number of times you throw what a die or what? Yeah, you throw a die is itself a random number. Let n be the random number. Number of dice thrown. Okay, so I just mean you are not specified this number, and this number could be 1, 2, 3, 4, whatever. Okay, so that's what you're. And let AI be the event. So let me not write A. Be the event that n is equal to I. You are given that probability of that occurring, probability of AI is equal to 2 power minus I. So of course I can take values 1, well I can take any value 1, 2, 3, etc. Notice that if you sum 1 by 2 by 1 by 2 power I going from 1 to whatever infinity, you get 1. Okay, so it is indeed a perfectly valid assignment. Okay, the sum of the score. So well, I mean, after you toss a capital N number of dice, you can consider the sum. Let S denote the sum of the uh, okay numbers thrown, numbers shown on the n dice on the dice. So there are n dice thrown, and you just look at the numbers and just add them up, and that is your value S, capital S. Okay. Find the probability that it takes a long time to state it, but it's well worth the time spending. Probability that any probability that n equals to Okay, given that S is equal to 4. S is equal to 4. Okay. Another, so B, n equals 2, given that, okay, sorry, that's what I just now wrote. Okay, given that S is equal to 4 and the first die thrown die shows 1. Okay. No, it's equal to given. Sorry, there is one more subdivision. I missed that. I write it as the third one. S is equal to 4, given that n is even. So it's a very nice problem. If you are already told what is n, then there is nothing to it. Okay. But you are asked to find the probability that n equals 2 or something happens. Okay. It's the other way around. Let us do this problem. So we know that, answer. So S is equal to sum of the numbers shown. Numbers shown. And that's equal to 4. So how could it happen? So what are the possibilities? So 4 you could have had, so just write the partition. You could have thrown like this, plus 1, and what is it? Next, or, okay. So I wrote 5, I think, sorry. In other words, you throw this thing, so A4, and you have this, so you could have thrown 3 dice, A3 and, okay. So you can have 2 plus 1 plus 1, or 1 plus 2 plus 1, or 1 plus 1 plus 2. Okay. And A2, it could be that A2, that is n equals 2, and so you have 2 plus 2, 1 plus 3, 3 plus 1. These are the possibilities. I should perhaps write ordered tuples, but anyway, I wrote like this. And then A1 and what? So you have 4. Just throw a 4. Okay. So what we need is, what is asked is, what is the probability that A4 has occurred? Sorry, let's see the question again. N equals 2, given that S is equal to 4. So n equals 2 means A2 has, sorry, I should write here not A3, but n equals 4. N equals 4, n equals 3, n equals 2, n equals 1. In other words, we should write everything in terms of tuples. Okay. But let us write what we want. So let us just fix the sum to be 4. Okay, I'm going to write that as 4. Sum of numbers equal to 4. remove this. So n is equal to 2, given that S4 has happened. Okay. Now you do it the other way around. Probability of this is same thing as probability. Whatever is easier, you write it in terms of that. Given that n equals 2 times probability of n equals 2. No? I think this divided by, n equals 2 divided by probability of S4. Okay. And again, probability of, so this is what you have to compute, right? But this is all, now everything is easy. Probability of S4 given n equals 2 is, okay. So n equals 2 is here, all right? I just underlined that. And the number of favorable things, events, so elementary events, that is 3. 3 elementary events can give you that. Okay. So that is going to be 3 divided by, well, in how many? So this is, what is 3? So S2 is equal to that 4. Sorry, S4 given N2. Given N2. So when n equals 2 is just 2, 2, 3, 1, 1, 3. That is 3. And total possibilities, there are 36 possibilities. Okay, so 3 by 36. What about this one, probability that n equals 2, that's same as probability of the event A2, which is equal to 1 by 4. Yeah. And what about the last one? So I should write here. So you can write probability of S4 is equal to probability of S4 given that A1 has occurred times probability of, so instead of writing like this, I should write maybe A2 and so on, but anyway, you understand, plus probability of S4 given A2 times probability of A2 and so on and so forth. Okay. So it's actually typically an infinite sum, but you see that since probability of S4 given AJ, S4 given AK equals 0. If K is already exceeding 4, you don't get anything. We have only a finite sum, and in any case, you can compute that. P of S4 is equal to A1 occurs with probability half. These are, you are told this. Okay. And what is S4 given A1? That's just 1 by 6, because only one favorable event. 1 by 6 plus S4 given A2. For A2, there were 3 of them. 3 favorable elementary events were there. So 3 by 36 times, well, what is probability of A2? Probability of A2 is 1 by 4 plus, what about 3? For 3, there were how many? Yeah, here again 3. 2 plus 1 plus 1, 1 plus 2, 3 of them. So 3 by 200. 3 by 6 cube, which is 216 times 1 by 8 plus Okay. The last one is 1 by, well, 2 power 6 power 4, the only one favorable thing, times 1 by 16. That's it. Therefore, the required probability that a 4 has happened, but this is same thing as probability n equal, sorry, we want probability n equals 2 or n equals 4, n equals 2. Okay. What did we want to compute? Yeah, n equals, we wanted to compute n equals 2 given that S4 has happened. So we have everything, both the numerator and the denominator, you substitute and find out. So A2, so I just erase, A4 has happened given that the sum is 4. This is n equals 2 given that S4 has happened. This is, well, this whole mess, whatever it is, you can compute it. It's not really such a big number, but anyway, I'll just leave it at that. P of S4, whatever this number is. In the numerator, you already have this calculated. 3 by 36 times 1 by 4. Okay? 3 by 36 times 1 by 4. If you want, you can simplify it later. All right. There's another problem which I want to work out. Maybe a simpler problem. Fair coin is tossed. So this I will probably not discuss in full detail. You try it today at home. Fair coin is tossed n times. It's a simple problem. What is the probability that on the nth throw, head appears for the first time? Well, you can even compute whatever you want. Head appears. Let me say for the second time. B. Number of heads is equal to number of tails, assuming n is even, n equals to m. Okay, even. Okay, so I think this is a fairly simple problem which you will all be able to do, I'm sure. But try it. And if you have difficulty, please get your doubts cleared during the tutorial hour. Okay. Now I want to talk about products of measure probability spaces. So in an intuitive sense, we have been using it, but we want to make it more formal now. So suppose that omega 1 f1, well, hey, so p1 strictly speaking, yeah, and omega 2 f2 p2 or probability spaces. Okay, so you want to make a product space, you want to make See, it's like tossing the coin first time once, and then whatever F1, all possible subsets of H and T. Omega 2 could be rolling a die. Okay, and then this will come with some collection of subsets of 1, 2, 3 up to 6. And P1 and P2, suppose you are given that. Then you may want to form omega. So let omega equal to, you want to make product, let omega equal to omega 1 cross omega 2. You want to make this into a probability space. Okay. And okay, so the important problem is, you see, the thing is, if you just look at, it turns out, so it's easy to see, easily seen that F1 cross F2 is not a sigma algebra or a sigma field. It's not a sigma field. It doesn't satisfy the requirements for something to be a collection of events in a probability space. Okay, like if you recall, for this to be satisfied, empty set must be the whole there, and so let's call this F. Okay, I don't want to call it anything. Okay, so it should be closed under countable unions, and it should be closed under complementation. The thing that fails is actually complementation. So let us draw a picture and I will show you why it fails under complementation. So you see, just think of omega 1 like this, omega 2 like this. So unit interval, it could very well be unit interval after all. Okay. So this is 0 to 1. Bad diagram, but you have to bear with me. And I could take maybe an interval here like this. This is my A and this is my B. Or let me write it A1 and this is my A2. And what is A1 cross A2? Okay, by the way, I didn't say what is F1 cross F2. What is F1 cross F2? This is an obvious definition. It's a collection of all A1 cross A2, A1, AI in Fi. Okay. This is a natural thing you would expect to want, to be collection of events, but it is not. Why? Because when you have this product, this is of course very much in there. Okay. So this is very much there, but its complement is not a product. Okay. So when you look at something like this, and a set in this one will look like union of rectangles. Okay, where you also allow possibly typically something like this. So a set here, something you can have a vertical strip also is possible. Omega, the second coordinate is arbitrary, so it could be like this, or it could be like this also. That's also allowed. But you see, even yeah. But if I take a rectangle, small rectangle like this, and take complement, yeah. But just 1 second. Maybe for this rectangle, it's okay. Perhaps it can be written as a union. But I have not said okay. So maybe this is also okay in this case. But if I take if let me say that if I take an arbitrary union, sorry, not arbitrary union, some countable union of these things, and then take complements and then take product, this is not closed under that. So it may be that we may be able to manage with
so you were telling that the countable intersection, since it isn't there in the product space, so if you consider the countable union of rectangle and take then complement, and
That will not be there. That's exactly the problem. You see, you can take countable. See, by taking countable unions, uh, you can form really strange spaces. I mean, for example, okay, let me say this following thing. So you can express interior of a disk, okay, as a countable union of rectangles, okay. But if I write
I think this example can be extended. Like
this
if you
example
consider
can be okay, no problem. But sorry,
a length
so
half, then geometrically the square is decreasing, and the complement won't be accountable. Like cannot be
absolutely,
formed.
that's exactly what I wanted to say. So you see, if you take this in this case, it's okay. But I want to take countable unions of this. So this can be exhausted. Interior. This is interior of a small disk. Small disk is expressible as a countable union. Union of rectangles. But the complement cannot be expressed as a countable union. That's what I wanted to say. Okay. But the complement cannot be expressed as its complement. Is not. Okay. In F cross. Okay. Actually, if you just honestly take only this one is not even closed under finitely, it's not even closed under union. Not closed under union. This is what I wanted to say in the first place, but I got digressed. Under union. Even finite union maybe. Okay. So if you look at the complement of this rectangle, it's a union of rectangles, all right. But it cannot be expressed as a product. Okay, if it is expressible as a product, look at the projections and they will go to the right subsets, but it's not. If you look at the complement and project it to the sides, you get the whole spaces 0, 1 and 0, 1. And that itself, so not even closed under finite union, there itself it fails to be something. So what do you do? Therefore, so in order to obtain a sigma algebra, sigma ring, I am using sigma ring that contains, okay, that goes with the product omega 2. We saturate, this is the main thing, we saturate F1 cross F2 so as to obtain a sigma ring, which you may call, well, some notation is needed, G of F1 cross F2. What do I mean by this one? So by definition, so this is, I just say saturate. By definition, you may say it in the following way. So by definition, G of F1 cross F2 is the smallest sigma algebra. Sigma ring. I keep saying sigma algebra. Sometimes they are also called sigma ring that contains F1 cross F2. Okay, so that you sort of expand it, your collection, but not too much. You want to sort of have the smallest one possible, which will have F1 cross F2. This is what we have to say. Okay, now how do you know that such a thing exists? You can do the following thing. You take, well, first of all, you need to know there exists some sigma algebra which contains F1 cross F2. It's sure it does. You take all possible subsets of capital omega, that will be a sigma ring, and that contains F1 cross F2. Now what you do is, so therefore, G F1 cross F2 is by definition intersection of all possible sigma algebras. G contains F1 cross F2, and this is of course contained in power set of omega. And G is a sigma. G is a sigma ring. I showed you there is at least one member in this family, so it's not an intersection over an empty set. That would be horrible. But this is how you do it. And of course, intersection you can always check is a sigma ring if each member is a sigma ring. Therefore, by definition, this is already a sigma ring. Okay, in fact, sigma is this one. So here I write here where the intersection is over sigma rings. Okay, so I'm not just saying that all possible subsets containing this family, but sigma rings. Okay, all right. My time is almost finished, but what about probabilities? So I have not yet completed that. P, so it's enough to just say what it does. So P of, you define, so define P of A1 cross A2 to be P1 of A1 times P2 of A2. Remember, P1, P2s are probabilities for omega 1 and omega 2. So this, you have defined it only for the products, but this extends to yield a function, probability function P from this collection G of F1 cross F2 to 0 to 1, which satisfies all the axioms of probability. Notice that when you take product of two numbers, both less than 1 and both are non-negative, you again get a number of the same kind. Okay, so how do you do this? Well, you need to, okay, so I mean, so at the moment, I think that to elaborate on this will take a lot more time, but more than that, it's not so easy. So we don't go into it at the moment. Okay, this is not an easy construction, by the way. This requires a lot of explanation. What we do understand is when you have okay, let me say it in the later on when we work with the specific situation, P will be clear from the context, or I'll explain what it is. To elaborate on this in the most general situation will be taking us too far away from these elementary considerations that we are at. So it's not easy. So nevertheless, this does determine. Okay, so all right, I think I should stop here for today. Yes.
So G is the Borel sigma algebra, like such a term.
Yeah, I should not be using. See, we have not said what are open sets and so on. Borel sigma ring. I mean, that concept we cannot talk about now.
What more is needed? Like they should be open.
But you need a topology to be able to say what is an open, or at least you need a metric space. For us, omega 1, omega 2, they are all abstract, I mean, given sets. Okay?
Measurable.
No,
Visual
I mean, no, we don't bring in the notion of measure anything here. You can say that our function P, gives you a notion of a measure of, you can say that it defines a probability measure on omega 1, but that's a language which we want to avoid. Okay, I have written down what are the axioms for the probability. It is indeed the case that the axioms I wrote down are very special kind of example of a more general notion of a measure space. But we don't talk about it in this course most of the time. Towards maybe the end of the course, later on, when things become absolutely essential, I will give a more broader picture of what is going on. At this stage, we don't talk about Borel sets or anything like that, okay, or Borel measurable sets or anything like that. This is, everything is, whatever I have talked about at the moment is self-contained, except I haven't told you how to get a probability function out of it. There is a unique way in which you can extend it so that this one gives you probability space. So this is our product space. So let me finally summarize. Sorry, I'm taking time. So omega 1 cross omega 2, and then G of F1 cross F2, and then you take this particular P. The book has a notation for it. I will not use that notation. I'll just use this P. You see product space. Product probability space. Okay, so let me stop here. Okay, so I'll stop sharing and we meet on Monday next week.
Thank you, sir.
Yeah, thank you. Yes.
Thank you, sir.